This video is going to discuss binary relations. But first, let's remind ourselves about what the Cartesian product or cross product of two sets are. So let's say we have set A, which consists of elements 1, 2, and 3, and set B, which consists of elements A and B. Then the Cartesian product of A and B is the ordered pairs 1A, 1B, 2A, 2B, 3A, and 3B. We can also find the Cartesian product of a set with itself. So A cross A, using this same A, could be written as A squared, and then it's going to be 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. If you've had set theory, you should already be familiar with some of this. A binary relation from a set S to a set T is a subset of S cross T. Now, we can find a binary relation where S and T are really the same set. That's what we'll do in our examples. But the binary relation is a set R of ordered pairs that satisfy some relationship between X as an element of S and Y as an element of T. So when you write X capital R Y, that's equivalent to discussing the ordered pairs X and Y that are elements of R. Now note that some authors use R like this. Some authors will use the Greek character rho, which sort of looks like a P. So in that case, they would have X rho Y in place of this. All right? So like other sets, depending on your situation, R may be described using some type of verbal or written description, which is, for example, X R Y means that X is less than Y. Or they may just list all the elements of the set. That is, for whatever this relationship is, those ordered pairs that satisfy this relationship would be 1, 2, 2, 2, and 2, 3. Obviously, if there's an infinite number of ordered pairs, for example, if we said X and Y were both elements of the integers, well, there's going to be an infinite number of ordered pairs such that one integer is less than another integer. We would have to use a verbal description in that case. We wouldn't be able to list them all. Now, what we're actually interested in is what we're getting to now, and that is relations can have properties. So let R be a binary relation on S. That means that we'll use S cross S as the Cartesian product. Now, R is reflexive if, for all X, X is an element of S implies, so we're having an implication here, X is an element of S implies that X comma X is an element of the relationship. So let's say, for example, we had this. We had S was equal to 1, 2, 3. And for whatever the relationship is, what it ended up producing was this set of ordered pairs. Is that reflexive? Well, no. This right here says that if X is in this set and 1, 2, and 3 are on this set, it says then we have to have all the ordered pairs such that we have X comma X. Well, we have 1, 1, we have 2, 2, but we're missing 3, 3. So this would be not reflexive. If R is symmetric, then that's the case when we have for all X and for all Y, X is an element of S and Y is an element of S, and X comma Y is an element of the relationship. Okay, then that implies that Y comma X also has to be an element of the relation. So let's say we have R's like this. 1, 2, and 2, 1. Well, we have 1, 2. So that says in order for this to be symmetric, we have to also have 2, 1. Well, we have that. And likewise, you could look at it and say, well, if we have 2, 1, we have to also have 1, 2. So this would be symmetric. If we also had in here, say 3, 4, well, since there's no 4, 3, that would be not symmetric. Another property is to be anti-symmetric. And note that, put it right here, not symmetric symmetric, excuse me, does not equal anti-symmetric. They're not quite the same thing. So anti-symmetric says that for all x and all y, if x is an element of S and y is an element of S, and x comma y is an ordered pair inside R, and y comma x is an ordered pair in R, then that must be that x is equal to y. So let's say that we had something like this. Is that anti-symmetric? Well, the 2, 2 here helps us out, but the problem is 1, 2, 2, 1. This says that if you have x comma y and y comma x, then it can only be because x is equal to y. Well, that's not the case here, so this shows that this is anti-symmetric. If we'd only had this, where we have a 1 comma 2, but we don't have a 2 comma 1, but we do have a 2 comma 2, and nothing says that we can't use 2 comma 2 here and 2 comma 2 here. This would be anti-symmetric by removing this. You may look and say, well, gee, but I've got 1 comma 2. Sure, but I don't have the 2 comma 1 that's necessary for the left side of the implication to violate this requirement here. And finally, being transitive says that for all x, for all y, for all z, if x is an element of S, and y is an element of S, and z is an element of S, and x comma y is an element of R, and y comma z is an element of R, then we must also have x comma z is an element of R. You'll see this for things like, say S is the integers, right, capital Z. And so we have the relationship that XR is equivalent to, say, X is less than Y. Because if we produce this, of course, there's going to be an infinite number of things, but R is going to have things like this, 1 comma 2, because 1 is less than 2. It'll have 2 is less than 3. It will also have 3 is less than 4. And we know that 1 and 2 and 2 and 3 means that, excuse me, this should be this, to do this. That would also be in the set, but it's not part of this example. 1 comma 3. We know for this relationship here that if 1 is less than 2 and 2 is less than 3, then 1 has to also be less than 3. So that would be in this set, right? There's going to be an infinite number of things, like I said. Or sorry, this should be this. We know that, like I said, if 1 is less than 2 and 2 is less than 3, we know that 1 has to be less than 3. So that would be a transitive relationship. Let's look at a couple more examples. Let's do like a smaller version of that. And we'll say S is equal to 1, 2, and 3. So the cross product of that, or the Cartesian product, would be 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. And let's use that relationship we just had, which is that the relationship between x and y is that x is less than y. So R here will be, or let's actually, we'll make this to test it out. X is less than or equal to y. So we have 1 is less than or equal to 1. 1 is less than or equal to 2, and 1 is less than or equal to 3. What about 2, 1? Well, 2 is not less than or equal to 1, so we won't have that. We'll have 2 is less than or equal to 2. 2 is less than or equal to 3. 3 is not less than or equal to 1. 3 is not less than or equal to 2. But we do have that 3 is less than or equal to 3. So is this reflexive? Well, if it is, we would have to have 1, 1, 2, 2, and 3, 3. There's 1, 1, there's 2, 2, there's 3, 3. So yes, this is reflexive. What about symmetric? Well, I have something like 1, 2. Is there a 2, 1? No. So example would be 1, 2 says that we should also have 2, 1, but we don't have that. Anti-symmetric. Well, this happens to be yes. Because if we take something like 1, 1, and we take the reverse of that, which is also 1, 1, that's only because 1 was equal to 1. And the same thing for 2, 2, and 3, 3. And then what about transitive? Just like we saw in the earlier example, we know that if 1 is less than 2 and 2 is less than 3, then 1 is less than 3. Does it matter that we don't have like other numbers, 1 and 4 or whatever? No, it's just for the ones that we have in the set. So really there's only one example where we show the transitivity, because we can't do 2, 2. Well, actually we could have 2, 2 and 2, 3. And of course take the first number here, last number here. That gives us 2, 3, which of course is what we had here. We could do that for a couple others. 1, 1 and 1, 2 says that 1, 2 should be there. Okay, we have that. And others, but we have that right there. Some of these, though, aren't always so clear. So let's look at a couple of cases that will demonstrate some things. But let's remind ourselves first what implication is. So we have a truth table. It says if we have A and B, then A implies B has this truth value. So if A is true and B is true, then this will be true. If A is true and this is false, this is false. But we have two other cases. We have false true and false false. If you remember for the implication table, these are considered true, these last two. If A here, what's on the left side of the arrow, is false, regardless of what B is, then the overall conclusion is that it's true. Okay? So let's look at some examples where we compare symmetric to anti-symmetric. Because remember I said that anti-symmetric does not mean not symmetric. So we'll just look at the relationship, and we're not going to talk here about being reflexive or transitive. We're just looking at these two for this case. So R gives us this. 2, 3, 3, 2, and 4, 5. Now here I have 2, 3, and 3, 2, which we would need for it to be symmetric. But we also have 4, 5 with a missing 5, 4. So this is not symmetric. What about anti-symmetric? Well, the fact that we have 2, 3, and 3, 2, but 2 does not equal 3, says that this is also not anti-symmetric. So this is neither. Right? Look at this example. All we have is 2, 3, and 3, 2. Now this is symmetric. We have 2, 3, we have 3, 2, or you could look at the other way. We have 2, 3, we have 3, 2, and 2, 3. You can go either way. But since 2 does not equal 3, just like before, this is not anti-symmetric. So what about this? Well, we have 2, 3, but we're missing 3, 2. So this is not symmetric. But it turns out it is anti-symmetric. So how can that be? Well, remember what we had when we looked at the relationships for anti-symmetric. It says for all x and all y, and remember how implication works. It says if you have the left side, that implies the right side. So here we have an x comma y, and y comma x implies x equal y. But we don't have an x comma y and a y comma x. We only have one of these. All I have is 2, 3. So basically we're saying something like this. We have a 2, 3, but we're missing the 3, 2. So this side is false. And so it doesn't matter what the right-hand side is. The overall implication is considered true. I know it's mind-blowing, but it comes down to understanding what the logic table for implication is. The left side is false, so it doesn't matter what the right side is, right? Because both of these are true when these are false. Look at this one. We have 5, 5, and 6, 6. So, once again, if we're looking at for symmetry or symmetric, it says if we have x, y, then the reverse of those two things has to also be there. Well, if we use 5, 5, the reverse of that is also 5, 5, so that's fine. 6, 6, the reverse of that is 6, 6, so this is symmetric. What about anti-symmetric? Well, turns out that when we have the reverse, it's only because they're equal, so this is also anti-symmetric. So once again, the first example is not symmetric, and it's also not anti-symmetric. The second one is symmetric but not anti-symmetric. Third one is not symmetric, but it is anti-symmetric. And the last one is both symmetric and anti-symmetric. If you're doing homework or something, you also probably will see something like this. R is equal to the empty set. Well, it turns out, for the same reasons we talked about here, right here with the false leads to something, right? Well, it turns out that's symmetric, anti-symmetric, and transitive. It would be all those, but it is not reflexive. Because for being reflexive, it says for whatever the set that we produce the Cartesian products from would have to have all those elements here as ordered pairs, right? So 1, 1, 2, 2s, those type of things, for whatever it is. Let's look at a couple of transitive examples. And we'll call this 5, actually. Call this 6. We're only looking at transitivity. Four, 2, and 2, 3, but where's the 4, 3? So we're missing 4, 3, so it's not transitive. Right? Because once again, if we go back to the logical description, if we have x, y, and y, z, then we also must have x, z. Now, if we look at 7, for logic similar to what we did on number 5, if we have r is equal to just, say, 4, 2, this is transitive. Why is that? Well, we have something like this. We have an xy, but we need a yz as well. We don't have that, so the left side is false, so it doesn't matter that we don't have XC. This right here is false. So this tells us the overall relationship is true, so it is transitive. All right? So those are binary relations.